In section 5.1, we learned how to use Riemann sums, which was rectangular approximations, to approximate area trapped between the graph of a function y equal f of x and the x-axis on a closed interval from a to b. We were picky, though, and said that f of x had to be above the x-axis for this entire interval. What we want to take a look at to begin with in section 5.2 is what do we do if f of x actually has some negative values. So we're going to take a look at a Riemann sum, and we're going to do a midpoint sum just to have a place to start. So let me partition my interval from a to b up into equal subintervals. Okay, that's pretty close. Those aren't perfect, but that'll do. So we've learned that x sub 0 is the left endpoint of the first subinterval, x sub 1 would be the next endpoint, and then we've got x sub 2, x sub 3, and the last one is x sub 4. So I've partitioned my interval from a to b up into 4 equal subintervals. Now, choosing the midpoint of each of these subintervals as the sample point. So that's the midpoint. That would be sample point x sub 1. And about right there is the midpoint. That would be sample point x sub 2. About here, there's the sample point for the third interval. And roughly there would be the sample point for the fourth interval. We're then going to use those midpoints to determine, let's go with blue, that'll be fine, the height of each rectangle. Oops, that's not what I wanted. I want a dotted line. There we go. Now, notice that those two intervals, the second and third subinterval, when we plug in the sample point, we get a negative value for f of x. Well, that's okay. So the whole point of this was to draw in some rectangles, so let me get in here and get some rectangles drawn. And I'm going to pause the recording while I do that. Alright, so here are the rectangles generated when we allow each sample point to be substituted into the function f of x to determine the height of that rectangle. And if we think about how we calculate the area, or how we estimate the area trapped between the function and the x-axis. Hang on. Alright, so if we think about how we calculate the area, we look at this first rectangle, and the area trapped between the curve and the x-axis is going to be approximately equal to f of x sub 1, sample point x sub 1, times delta x. And then we look at the second triangle, the second rectangle, which happens to be here, and we're adding f of sample point x sub 2 times delta x. And then we look at the third rectangle, which would be this space here, and that area would be f of x sample point x sub 3 times delta x. And finally, the fourth rectangle's area would be found by taking sample point x sub 4, plugging it into f of x, and then multiplying by the width of that interval. Now what's different is f of x sub 2 and f of x sub 3 are negative. So when we actually multiply f of sample point x sub 2 and f of sample point x sub 3 by delta x, those rectangles, or that product, is a negative value. So a Riemann sum, we can think of it as assigning a negative number to any area that's below the x-axis. And that's absolutely okay when we're working with with definite integrals and being estimated by Riemann sums. What we're looking at there is something called the net area, which is the same. Some books refer to that as the signed area. The net area trapped between a function and the x-axis is going to be the sum of the areas above the x-axis minus the sum of the areas below the x-axis. So if we're looking at that picture right there, that net area would be the area A sub 1 minus the area A sub 2 plus the area A sub 3. Now we know that a Riemann sum gives an approximation for signed area, and the more subintervals we can squeeze into our interval from A to B, the closer our approximation would be. So again, the approximation values are going to get closer to the actual net area if we allow n to approach infinity. So if n, which is the number of subintervals, gets closer to infinity, the width of each subinterval is getting closer to 0. And if we allow the width of each subinterval to get closer to 0, the approximate area will be getting closer to the exact area. In both of these cases, we're talking about a net or signed area. Now, in all the problems that we've done so far with Riemann sums, we've been using a regular partition where we divided our subintervals up equally. We don't actually have to use a regular partition, though. We can use what's referred to as a general partition. And in a general partition, we divide the interval from A to B into subintervals, and these intervals are not necessarily the same length. They might be, but they don't have to be the same length. So if I'm going to do a general partition for this particular interval, I might let x sub 1 be right there, and maybe x sub 2 is way over here, x sub 3, x sub 4 right there, and let's let this be x sub 5. So I'm going to have 5 subintervals. Okay, and clearly they are not all the same length. And then we choose some sample point in each of those subintervals. Again, it could be the midpoint of each interval, it might be the left end point of each interval, it might be the right end point of each interval, or it can be just some other point. So I'm going to choose that as sample point x sub 1, and maybe this point as sample point x sub 2. There's sample point x sub 3, sample point x sub 4 right there, and maybe sample point in the 5th interval here. Now again, we're going to let these sample points go into the function to determine the height of each rectangle. Alright, so there are the 5 rectangles that we're going to use to approximate the area under this curve. Now we know that we can call this net area. So in this case, the net area would be approximately equal to f of sample point x sub 1 times the width of the first interval. So delta x is not going to be the same. The width of the interval is not going to be the same for each one, so we have to designate that with the subscript. Alright, so that was this area. The second rectangle's area would be f of sample point x sub 2 times delta x sub 2. The next rectangle's area, the third one, would be f of sample point x sub 3 times delta x sub 3. The next one, f of sample point x sub 4, which is negative again, times delta x sub 4. Okay, and I'm out of room, so I'm going to come down to the next line. No, I'm going to make it squeeze. This is how I do that. Oh, stop that, come back. Here we go. Boop. And I can scoot that over just a little bit, where now I have room to write the area of the fifth subinterval would be f of sample point x sub 5 times delta x sub 5. And that is this rectangle. Now, we've got to think about what happens as n approaches infinity. Well, the width of each sample point gets closer to 0. So and that's for all widths, for all subintervals. So here's how we're gonna here's how we can handle that notation. We're gonna let just delta represent the largest delta x sub k. So here's how we can think about that. As the largest interval approaches 0, all the subintervals, the widths, have to be approaching 0. And that's going to be true for all k, 1, first subinterval, second subinterval, and so on, all the way out to the nth subinterval. So the net area, and I'm going to use my summation notation, will be the limit as delta approaches 0, as the width of the largest subinterval approaches 0, of the sum, if k starts at 1 and goes to n, of f of sample point x sub k times delta x sub k. And this limit is called the definite integral. So if we want to define a definite integral, we use the integral sign notation with the limits on the intervals from a to b of f of x dx. That is, by definition, the limit as the width of the largest subinterval approaches 0 of the Riemann sum. Now we say that if this limit right here exists, then the function is integrable. As far as the notation goes, this integral notation right here, the function f of x is called the integrand. Of course, the stretched out s is the integral sign. A is the lower limit. B is the upper limit. And the differential dx tells us what variable we're using.